I thought what we could do is stop here, and since we're going to talk about the paper, let's stop, bring the paper out, and let's talk about that for a while. And next time we'll finish that up, and we're going to start in chapter 4 next time. We'll be done with chapter 3, so you might want to read ahead in chapter 4 and get ready for that. And what we'll do is, can you bring do you know how to bring up the sound on the people?
I can try it real quick.
Why don't you guys say something down there so they can discuss amongst yourselves. Come on, Laura, say something.
Somebody.
Me.
Keep talking.
I'm the professor here.
I think I've got it.
All right. Well, the one I've got is this one here, the amperometric microsensor for H2S and aquatic environment. That's everybody else's one, I hope. I didn't screw that up again. Any particular questions that people had before I start? I had a few questions, but I'll just let people ask questions and see what's going on.
Can you explain the part where you said measuring setup and procedure?
Mm-hmm.
That beginning that said that the microsensor was connected to a homemade pico ammeter and an internal voltage source to polarize both working electrode and guard electrode. Why do they do that?
Right. Well, first of all, let's make sure we understand what the title means, and that's often important. And then we'll explain that in a minute. But what's that word amperometric mean? Does anybody know what amperometric means? Yeah. So amperometric is got the word amp in it. That's current versus we're measuring current basically. So amperometric means we're measuring current. And now, some sensors, particularly pH sensors, for example, are not amperometric. They're so-called potentiometric sensors. And this is a potentiometric sensor that measures potentials. This one measures current. So amperometric current measurement sensors often have to apply a voltage to polarize it to get current to flow. Otherwise, we would just sit at the equilibrium point and not get any current flowing. So microsensor, that's kind of a made-up word. That just means a small sensor. Termination of hydrogen sulfide in aquatic environments. All right, so going back to your question, a picoammeter is just a sensitive ammeter. That's a small current source or current measurement device that can measure currents down to picoamps, 10 to the minus 12th amps. They're saying that they have an internal voltage source to polarize both working electrode and guard electrode. And that just means that there is some sort of voltage source, maybe from a battery or something like that they can apply 150 millivolts or so. And it needs to be polarized. We use the word polarized to suggest that there is a potential versus the counter electrode in that particular case. So that polarization is required to get current to flow. So you can think of it as an overpotential for that system. And without a current, without a potential being applied, we would get no current to flow in this particular case. And we need some current flow because how does the experiment work? Did you get that? I mean, you can see on scheme 1 a basic diagram of the system. That'd be on page 4353. What's the function of the silicone membrane in the system? What's that doing for us?
Reaction.
Your salt bridge, so to speak?
No, it doesn't really do that.
Separates to the charge. It passes the charge species.
Right. Well, let's think about what we're trying to measure. They're aquatic environment. They don't really say what they're measuring, but actually what they're probably interested in doing is putting these in either mud at the bottom of the ocean or some lake or something like that, and the mud from microorganisms is got hydrogen sulfide in it. It's a product of their metabolism. So thinking about it that way, why would we want a membrane in there, in that cell? What's that doing for us?
Well, we don't want any particulates that are not related to H2S.
Right.
Impurities and
We could just put in a barrier there, though. We could just put it. So what else is that membrane doing for us besides keeping the mud out of the?
Making it easier. In this way, HS has to go through an electrochemical reaction at that level.
Yeah.
Okay, current. So
Well, you see actually, you see H2S sort of going up to the membrane there, and then it's suggesting that H2S is passing through the membrane, isn't it?
no, but never gets there.
Right. But H2S is a gas, actually, a dissolved gas in most cases. It's not a gas that you're seeing, but it's a dissolved gas in solution. So the H2S is going through the membrane as a gas. So the membrane actually is acting as a filter, if you like. It's only allowing gaseous material into the system. And why is that important? Because we don't want to, he doesn't want to measure HS minus or S2 minus. He wants to measure H2S. I'm saying he, maybe it's a she. I don't know. They want to measure H2S, not the other one. So the membrane not only acts as a barrier to keep it clean, but it acts as a gas barrier. So only gas diffuses across that barrier. And there's actually another gas that you might have to worry about in that case, and that would be oxygen. But they actually describe why oxygen is not considered to be a problem. Mostly the systems are anoxic. They don't have any oxygen present in the bottom of the ocean and the muds. So why don't they show H2S as being H2S inside between the membrane and the working electrode on scheme 1? What's happened there?
Ionizes to hydrogen and with hydrogen sulfide.
Right. As soon as that H2S gets in the alkaline sensor solution, it's no longer can be in acid form. So it ionizes to HS minus. So that's why they show it as HS or H plus S double minus. And it also supplies a gradient. There is also always a diffusional gradient. Because there's no H2S inside the membrane, there's always going to be a flux. If there is any H2S outside, it will diffuse readily into that system. What's the purpose of the iron? This complex iron FeCN6 3 minus 4 minus. What are those doing for us?
Ferrocyanide. The ferrocyanide is used to oxidize the sulfide ions to sulfur.
Yeah.
And then then the ferrocyanide are back oxidized again. And in this case, the oxidation current will be proportional to the quantity of sulfide ion present in the medium.
Yeah. Well, for our non-electrochemist friends, there's two complexes. There's FeCN6 3 minus, that's called ferricyanide. And then the FeCN6 4 minus is the ferrocyanide. And then the oxidized and reduced form is a complex. It's a stable complex of iron that's often used in electrochemical experiments. Why do they bother? What's the point of having, essentially what you're saying there is a mediated electron transfer. We're making the electrons flow from the electrode, or they're pulling them into the electrode from the ferrocyanide. And why can't we just skip the ferrocyanide and ferrocyanide and directly oxidize the sulfide? What's the purpose of having that ferrocyanide in it? It seems to be extraneous.
You're measuring the signal, aren't you? Got the reoxidation.
Right. But why couldn't we just measure directly the sulfide ion?
Maybe the concentration of the sulfide is very low, and we need an ultra micro electrode to do this.
No, that's not really why. It shouldn't make any difference. I mean, basically what you're doing, this is actually often the case, that you use a mediated process and sensors. And what did we talk about today? Why might we want to use a mediator rather than a direct process? Kinetics, yeah, that's a good thing. It turns out that the reduction of HS minus to sulfur is slow, very slow on most electrode materials. And not only that, the sulfur will absorb onto the surface and poison the electrode itself. So if we used a sensor that tried to directly do the measurement, what would happen is that first of all, we'd have to apply a very large overpotential for the reaction to proceed at a significant rate. And also we'd find that our sensor immediately quit working because it would be poisoned by the sulfur that we make, okay? So by using a mediator, we avoid that problem. The chemical oxidation by ferricyanide with HS minus is much more efficient. It's much more labile process, occurs rapidly. And so the kinetics for that is very rapid, and so we can easily then do the process at a much lower overpotential. So by using a mediated process, we can minimize the overpotential and also minimize the problem of poisoning. All right. What was the they talked about this. They talked about making it the sensor, and notice on table 1 the features. You can see the effect of what the zero current is. You can see that's very small, 2 to 40 picoamps. It drifts a little bit, but not too much. But this sensor is still not probably ready for prime time, but they're still developing it, so it doesn't work great. But you can see the limit of detection is about 2 micromolar, relative standard deviation about 2.5%. Does anybody remember how long these last? Yeah. Yeah. About lasts, you can see on figure 5, according to that figure, lasts about 30 days. It says microsensor has a maximum lifetime about 6 weeks. Actually, the couple limitations. One is the stability of the electrode, which will change with time. The other would be the ferricyanide itself. Once the ferricyanide runs out in the sensor, it will no longer work properly. And in fact, you really want to, it's not just that it runs out, but you want a high concentration relative to ferrocyanide to get the reaction to go. So as soon as the ferricyanide drops to some small fraction, or even a big fraction of what it was, it'll not work properly anymore. You'll need more and more overpotential to get the reaction to go. And you can see some other things. I'm not sure. A couple things. They had a problem with pH. Look on figure 10. It's on page 4356. Look at, you can see the current potential curve for that with the redox mediator present in the system. And you can see there's an equilibrium potential. And this is actually I think a German group. Yeah, and so they use U for potential. That's often the case for Europeans, especially Germans use U for that. But you can see there's an equilibrium point at about 0.22, I guess, 2.22 volts. There we're polarizing then at about at 0.2 volts to say 0.42 or something like that. So there's your polarization voltage right there. So you're going from that equilibrium point to a sufficiently positive to get the reaction to occur. You have to be, they wanted to be out on that plateau part of the wave. Okay. All right, well, we're going to ask ourselves some other questions. We'll see some things later that are important in this paper. One is diffusion. Now, how do molecules get from somewhere else into that sensor? The molecules have to diffuse in, and will the rate of diffusion have any effect on our sensor performance? And you might ask yourself, what would be the situation if we made our sensor bigger or smaller on the signal? Would it necessarily be better to make a bigger sensor than a smaller one? And we'll see some of that later on, what's going to happen. Well, I did have one question. Rhonda asked, she asked me what the purpose of the guard electrode was. Anybody see that? I think on page 43, I remember seeing it here. Page 4353, if you look on page, about halfway down, it says more details, especially the function of the guard electrode are given elsewhere. And does anybody remember reading that particular part of the paper? Does anybody have any idea what that guard electrode is doing for us?
A fixed value.
It would be like a reference electrode?
Not really.
The oxidation current's measured between the working and the guard.
Yeah.
We still have the counter electrode. At the beginning, I thought that this is another name for counter electrode, but I figured out there is a counter electrode.
Mm-hmm.
Yeah, if we thought about a reference electrode, that would really be where the CE would be. That would be the counter electrode in this cell, because usually when we use a reference electrode, we're measuring the potential versus at some point. So by applying the potential that we've applied is really versus that CE point, counter electrode point. It's kind of interesting situation. We're measuring the current. We're having the working electrode and the guard electrode essentially at the same polarizing potential.
Yeah.
But we're measuring the current difference between the two. All right. And I didn't read the paper, actually. I don't know exactly why, because in fact we don't get that paper on campus, so I couldn't look it up. But I have a theory, and this may be wrong, but my theory is this, is that notice how they've drawn it. I think you can see a better picture in figure 4. You can see the guard electrode there. It does not extend all the way to the bottom. The working electrode is very close to the end. The space between the working electrode and the membrane, they claim, is about 40 microns. And the space between the working electrode and the guard is about 200 microns. So there's a significant difference in the distance between the membrane entrance and the guard electrode. So what might you think would happen in that particular case? What would be the importance of having the guard and the working electrode at different positions in the cell? What difference would you observe?
Is the resistance between? There will be a difference in the resistance between the.
Yeah, there would be a difference in the resistance. What would that help with
sensitivity.
Remember, the guard and the working electrode are the same potential, so if there's a resistance difference, that wouldn't really make any difference, would it? What do we think about what we're doing? Okay, what's the point of the? So what's actually going on? Think about it physically. We're measuring H2S, so what's happening first in that process?
Diffuser.
Diffuses through the membrane, undergoes a chemical equilibrium to form HS minus, and then what's it do?
Oxidized.
Yeah, it gets oxidized,
Yeah.
and so where's that oxidized molecule at? Most likely.
Where the guard electrode
Is it where the guard electrode is?
The oxidized molecule.
Well, actually, we oxidize the HS minus, and so the ferricyanide is doing that job for us. So we make some ferricyanide when we do that. So we reduce the ferrocyanide to ferricyanide, right?
Mm-hmm.
So where's the ferricyanide being formed?
near the guard also.
Okay, the ferricyanide is being formed
The working electrode.
from the oxidation of HS minus. So where's the HS minus present? Yeah, it's near the membrane, right? As soon as it gets into the membrane, it goes, so that's where the ferricyanide is going to be. Okay? And so, in order to get a signal, that ferricyanide has to diffuse to the working electrode and become oxidized again. And ferrocyanide, yeah. And then, so the guard, I think what's happening is that the guard electrode is kind of keeps the spatial resolution okay. In other words, it acts as a stable point. None of the species that are coming in out of the membrane are really getting up to where the guard is ever at. And if it did, the guard would act still as a stable point. So there's a baseline current, and but we're only measuring the current difference between the working electrode and the guard electrode. So the working electrode is there right near the membrane, so that it will pick up the reduced species and oxidize it. And I guess I should say the ferrocyanide. Ferrocyanide is formed at the other side. Well, I guess we're out of time. So let's stop and the next paper is on the web page. I don't know if I handed that one out or not. I think it was one we handed out. So. Is on the web page. I don't know if I handed that one out or not. I think it was one we handed out. So.